Hi everybody. In this video, we are going to start solving problems from LeetCode Stop Interview 150 problem list. We are going to go down this list and solve one problem in each video. So today, let's pick the first one, which is merge sorted array. Okay, let's read the problem and make sure we understand it. You are given two integer arrays nums1 and nums2 sorted in non-decreasing order and two integers m and n representing the number of elements in nums1 and nums2 respectively. Merge nums1 and nums2 into a single array sorted in non-decreasing order. Okay. The final sorted array should not be returned by the function, but instead be stored inside the array nums1. I see. To accommodate this, nums1 has a length of m plus n, where the first m elements denote the elements that should be merged, and the last n elements are set to 0 and should be ignored. Nums2 has a length of n. Okay. So I think actually let's look at one example. I think I understand the problem, but just to confirm my understanding. So input is nums1 is 1, 2, 3, 0, 0, 0, but m is equal to 3, which means there are actually 3 elements in this that we care about, but there is space for 3 more, and that's because the nums2 array has 3 elements and n is equal to 3. They have given to us explicitly in another integer. And this is because we are supposed to merge the numbers of nums1 and nums2. Well, the numbers in nums1 is just first 3 into the nums1 array, and that's why there is extra space at the end. In fact, these could be junk, right? And we should still work, our program should still work instead of initializing to 0. But well, Java initializes all integer arrays by default to 0, so they must be zeros. Okay. The arrays we are merging, yeah, I just talked about that, so they're just explaining that. Sounds good. And I think, okay, let's look at the example 2. In this case, nums1 is just one element. I see, so nums2 is empty, and that is denoted by n equal to 0 as well. The array is empty, and there is nothing to merge. We just, keep nums1 as is, which is just 1. And in example 3, oh, wait, okay. Oh, actually, this is a flipped example of example 2, where nums1 has 0 elements, logically speaking, but it needs extra space for all the elements in nums2, but then nums2 has only one element. And that's why in this case also, we make nums1 contain 1. Basically, we merge this one into nums1. Okay, I think that makes sense. Let's look at the constraints. The constraints are that the length of the first array is equal to m plus n. Yeah, there is enough space in the first array to hold both the elements from both the arrays. And then the length of the second array is n, and m and n are between 0 and 200 inclusive, and m plus n is between 1 and 200 inclusive. Okay. And then the values in both the arrays are between negative 1 billion to positive 1 billion inclusive. Okay. Yeah, that's within the range of a 32-bit signed integer. Can you come up with an algorithm that runs in O of m plus n time? Yeah, basically linear time, right? That's what they're trying to say. Okay, so let's try to work this out. I'm going to take this first example to figure out what approach we might be able to take. Well, so I think to begin with, the way to think about this, at least the way I'm thinking about this is, imagine that we are actually just merging the results of these two into a third array, right? So let me actually take this in comments. So imagine that we are just not merging into nums1, but if we were merging into a third array, then I mean, that's a very simple algorithm, right? We basically do two different pointers. One is pointing in nums1, so let's actually write that down. So let's say we were just merging these two into a third array, right? Which has enough space, for example, right? So initially it has 1, 2, 3, 4, 5, and 6, right? And so what we do is we say, okay, hey, for the first element here, we just iterate through the output array, which is and keep a destination pointer there. which is pointing to 0th index in the output array, and we say, okay, which element should we pick from from the two source arrays, and we pick the smaller of the two, right? And the two source arrays also have a pointer each pointing to the index where we should read from. So since the first array has the smaller one, we pick that and we move the pointer forward here. So now the pointer is at 2 here, and the pointer is also at 2 here, right? Then we say, okay, hell, now we are at destination pointer pointing to the second element in the destination. Where do we pick from? Well, when they are equal, we can arbitrarily pick from any, but let's say we pick from the first array. So we move the pointer forward to 3, this one, and here the pointer is still at the first element, right, in the second array, and so on and so forth. And ultimately, we just will copy all the elements in the right order, and that will be a typical merge. So that's how we generally do a merge into a new array if we are merging two different sorted arrays. Okay. In this case, the problem is if we do that here, now here they're saying we can't use a new array, we have to use it in place. So if we do that here, for example, let's say we have this, right? And let's say at some point, let's say if this was a, let's change the numbers, right? If this is a, this is 4 and this is 5 and this is 6 and this is 7. Okay, so let's say when we are put 1 stays as it is, but when we put 2 here in its right place, we'll have to push 4 and 5 one space to the right. And if there were many elements, not just 4 and 5, there was like 10 and 11 as well, then we are pushing many elements to the right, which is an O of n operation, right? In the worst case, we are moving a bunch of elements to the right, order of n elements to the right by 1. And then we do that, and okay, so if there was a 3 here, then we do that for 2, we shifted everything. So what will happen is we'll basically shift everything to the right, 1 0 at the end will be removed. But then again, when we are copying 3, we again do the same thing. So in the worst case, we might do that like O of n times, right, for n elements. So it becomes an O of n square algorithm. And that's why I think they have a follow-up saying, hey, can you do it in O of m plus n time or a linear time instead of a quadratic time? And yeah, so let's go back to our example here, the changed example. Well, I mean, in this case, probably a lot of you already kind of are thinking about this or figured it out is, since the extra space is at the end, why not start at the end, right? So what we do is we basically say, hey, start the source 1 pointer from the last number in array 1 and source 2 pointer from the last number in array 2. And let's pick the maximum and put that guy at the last index. So here it's 11, right, after the first iteration. Then this pointer decremented, the source 1 pointer decremented, because that's where we picked the bigger element from. So we say, okay, between 10 and 7 did not decrement because we haven't yet placed it in the right place. So we say, okay, 10 is still the bigger one. So we pick 10 and we move that pointer 1 to the left. And between 5 and 7 is the bigger one. So we say 7 is here, and then we move that pointer 1 to the left, right? And this is still at 5. Between 5 and 3, 5 is bigger. So 11 will be overwritten by 5. And that is, note that we don't have to erase 11, right? It can stay because it will ultimately be copied by the right value. And so now we are at 4 here, and we are at 3 in array 2. Between 4 and 3, 4 is bigger. So we do that, and we move that to 1. Now we are at 1 in array 1, at 3 in array 2. And so this will become 3. And similarly, this will become 2, and we would have merged. So we basically are pulling from behind rather than pushing from ahead. And the reason is because the extra space is at the end. If the extra space was at the beginning, for example, instead of that array, we were given like, oh, hey, the extra space is at the beginning. Then we don't have to push from behind. We can actually do from the beginning, right? 0, 0, 0. And then if we have 1, 4, 5, 10, 11, then we could actually start. Sorry, I'm missing a comma here. Then we could start from this 1 and this 2, and we can just start copying here, right? And that would work too. So just note that that is the common pattern. Like if you have extra space at the end and then pull from behind, If you have extra space in the beginning, then you can actually still just do from forward, right? So, okay, so let's try to implement that approach. And that would be the linear time approach, basically. Okay, so what are we doing? So we are keeping track of index 1. Index 1 starts at, again, we're pulling from behind. So where does it start from? It starts from m, but the highest index value is m minus 1. And index 2, these are the two source indices in our algorithm, is n minus 1, right? The largest index in the second source array. And then we have a destination pointer, but remember the destination is just filling up the whole array, right? So we basically can just initialize that in the loop. So destination starts with what? It starts with m plus n minus 1, the last index in the first array, which is the last index here, basically in our example. And then we say dest index is greater or equal to 0 minus dest index. Basically, we are just doing one loop which is trying to create the entire results array, right? Okay, now what do? We have, actually there is one short circuiting condition, but let's come to that in a second. Actually, I think, yeah, I think it will be good to write it now. And the short circuiting condition is as follows, right? So let me go back to my original example. Yeah, this one actually. So let's go back to this example, right? In this case, let's just change this to 3. Actually, let's make this 4, 3, 3, 4, 1, 2, 3, 4, 5, 6. Yeah, this is good. Okay. So in this case, let's say that all the elements here were bigger than all the elements in source 1, right? Or in the array 1. Then what will happen is we'll end up copying them here at 5, 6, 7, 5, 6, 7. And after that, we can actually stop. So if you have exhausted all the elements in the second array, that means in the first array, the remaining elements should be in the sorted order by definition. We don't have to continue writing them on top of themselves. So here, basically, what we need to do first thing is that if we have exhausted all the elements, if index 2 is less than 0, right? We are decrementing both the source indices because we are again pulling from behind. Then we say we break, right? We are done. We don't have to. So that's a short circuit. Otherwise, the loop goes on for the whole 0 to m plus n minus 1 inclusive. But otherwise, in this case, we break. Okay. So that's our short circuiting condition, but the remaining algorithm stays the same. This is just an optimization, right? Okay. So let's now do the algorithm that we talked about. We say, okay, when do we pick from source 1? I think that is the way to think about it. Well, when do we pick from source 1 is if index 1 is greater or equal to 0, which means it is within bounds, and nums1 of index 1 is greater or equal to nums2 of index 2, right? And in equal to, you can pick from either one, but in this case, I'm just picking from the first one, right? In that case, what are we doing? Pick from nums1, right? And so what do we pick from nums1? We basically copy that element and we say and where do we copy it? To the destination index, but that actually is an index into nums1 array. And we pick from nums1 from the source index 1, right? And remember, we decrement index 1. We cannot forget this, right? You could do index 1 minus minus here and not do this line at all. I generally avoid the postfix operators. They are a little confusing at times. So anyway, I like the simplicity of just doing it explicitly. Okay. So that's what we do there, and else, which means either we ran out of elements in nums1 array, or the nums2 array element is bigger. In both the cases, in that case, we pick from the second array. Still, we write to the same place, right? We always write to the same place. Dest index equal to nums2 of index 2, right? And minus index 2. There you go. Okay, so let's just review this one more time. I'll create a little bit more space here. Okay, so we started both the source indices from the last index of both the source arrays, and the destination index also starts from the last index and goes all the way to 0. We have a short circuit for optimization. If we have exhausted all the elements in the second array, we can stop. And if we are in bounds in the first array and that element is bigger or equal to the second array, then we pick from there. Otherwise, we pick from, well, I have a comment there. I should have a comment here. Pick from nums2, right? Okay. So I think that's our algorithm. Yep. And let's try to run this. Okay, I have a compile error. That should be easy to fix. Let's see what it is. And then, oh, okay, of course, nums1 of index 1, right? Okay, so those are accepted, though we should add a few more test cases, right? The ones that we talked about, a little bit bigger ones. So let's do that. Well, actually, let's add the case where all the elements here are bigger, like we talked about. And then we'll add one more test case where some elements are bigger and some are smaller. So let's say this is 30 and then this is 60, right? And we'll still keep that. Okay. There you go. Okay. So I think that makes sense. Just making sure it is, yeah. Okay, they are all sorted. So that's the O of n plus n algorithm. And again, revising it, like anytime we are merging sorted structures or sorted collections, this is a very common pattern. And in this case, the difference was, we had to do it in one of the input arrays and the extra space was the end at the end. So we had to pull from behind rather than push from the front. Hopefully that was helpful to all of you. If you're liking what I'm doing on this channel, please consider subscribing to my channel and please hit the thumbs up button on the video if you can. See you guys next time.